In Chapter 8 of Block 2, you will have encountered mass spectrometry. All astronomers are aware of the electromagnetic spectrum, but in planetary sciences, the mass spectrum of the elements is something which provides important information about solid materials. Mass spectrometers can be enormous, occupying a whole room, or they can be small, like this gas source machine. The feature they all have in common is the ability to separate mass by passage through a magnetic field. A mass spectrometer is made up of a number of components. There's a means of producing ions, and these ions can then become accelerated, where they leave the source via a slit, and then they pass through a magnetic field produced by this magnet, and they travel in a curved trajectory before coming to a detector or collection system which provides amplification. If the ions enter a region of constant magnetic field, they have the property of moving in a curve. Ions with less mass are bent more than those with more mass. By separating ions of different mass, we can learn what elements are in a particular sample. But perhaps the most important property of mass spectrometers is their ability to separate isotopes. In Chapter 8 of Block 2, we saw how oxygen isotopes can be used to detect heterogeneity in the solar system. Isotopes are forms of an element which have different mass because of differences in the abundance of neutrons in their nucleus. Oxygen has 8 protons with positive charge. These are balanced by 8 tiny negative electrons, which can be considered for our purposes to have no mass. The balance of the mass of oxygen is made up of 8 uncharged neutrons, so that in total the common isotope of oxygen is 16 mass units. About 2 out of 1,000 oxygen atoms are not like this. They have 2 extra neutrons to give 18 units of mass. And less frequently, about 1 in 2,500, there is only 1 additional neutron, so that there is a small fraction called oxygen 17. Before going on, use the table in your notes to work out all possible masses of molecular oxygen that can result from combinations of isotopes of oxygen 16, 17 and 18. What are their relative abundances? If oxygen gas is put into the mass spectrometer, it produces ions with masses of 32, 33 and 34, because 2 16s will combine together to give a molecule of 32, a 16 and a 17 to give a 33, and a 16 and an 18 to give 34. There are other combinations, but they're a very low abundance. Those ions, focused through the mass spectrometer, arrive at the collectors, and if you put 3 collectors, then it's possible to simultaneously collect all the ions of interest. To provide information about the isotopic composition of any sample, such as a mineral, a silicate or an oxide, we have to ensure that the oxygen is transferred to the gas phase. Sample preparation is of paramount importance because we have to make sure that all the oxygen is obtained and that no fractionation, that's artificially changing the isotopic composition, is introduced during the experiment. The technique is to displace oxygen from the minerals using very reactive fluorine gas at high temperatures. The procedure is to load small amounts, about 1 milligram or less, of selected materials into a carousel for investigation. The carousel is inserted into a vacuum chamber, and the samples can be selected by viewing with a video camera. The compound containing fluorine is introduced from a liquid nitrogen trap, and the meteorite for which data is required is heated by selectively focusing a laser through the optics of a microscope and scanning the beam backwards and forwards across the sample so that the reaction proceeds. The liberated oxygen gas is collected and taken into the mass spectrometer for measurement. When plotted on a graph of 17 oxygen, 16 oxygen against 18 oxygen, 16 oxygen, meteorite samples fall in various defined regions, quite different from Earth's rocks, which all fall on a trend called the terrestrial fractionation line. The reasons for such differences are discussed in Chapter 8. As I have already indicated, the minor isotopes of an element make up only a very small proportion. We have to be able to measure this abundance relative to the main isotope very precisely. The problem is that mass spectrometers are very different the world over. This mass spectrometer here is quite different from that one on the opposite side of the room. To overcome this difficulty, all the vacuum pipework you see here is to enable us to swap backwards and forwards between our sample and an internationally agreed reference material, so that the small differences can be measured and allow us to compare with results obtained elsewhere in the world and even in our own laboratories. The instrument swaps between the sample and the standard on quite a short time scale to obtain what is known as the delta or differential isotopic composition. We need to know this to fractions of a part per thousand. As I have already said, the approximate isotopic composition of oxygen 16 to 18 is about 500 to 1. To understand planetary processes, we really need to know whether this is 499.95 or 500.01 to 1.